multiplied by 0.00264. The copper losses at the full load is 400.
Awak pun pakai
For
loss lah.
tak,
Ni kan makin jauh suaranya.
tadi salah tu.
Apa yang
Tadi
salah? Saya pun tak tahu apa yang awak salah.
salah. Yang 1250 ampere tu it is the secondary current. So to calculate the copper loss at full load, we take the secondary current squared, multiply by 0.00264. So the copper losses at full load is 4125 watt. So at half load, we also use the same formula, but at half load we need to divide the current 1250 divided by 2, and we get the current at half load. So we do the same formula and we get the copper loss at the half load. Thank you.
Hello? Dengar tak? Hello? Hello? Hello?
Tak dengar tu, tak dengar. Ya,
Hello?
dengar.
Dengar. Okay. So the
Ya,
next
dengar jelas.
hello. Okay.
Ya,
So the next example
Hello.
questions is about what is the
ya,
efficiency.
dengar jelas.
Hello. I repeat. Okay. Right. So the example question
Ya,
next is what is the efficiency of the non-ideal transformers. So on our question, we have the circuit of non-ideal transformers. We have primary part and secondary part. So on primary part, we have 120 volt that's classified by V and 20 milliampere for I. And the secondary part, we have 15 volt for V and RL is 100 ohms for R. So how to find efficiency in this non-ideal transformers? So we need to use the formula that has been explained by our group just now. There is N equal to P out over P in times 100%. So how to find P out and P in? So we have three choices to find power. There is P equal to VI and P equal to V squared over R and P equal to I squared R. So at the P out session, at the secondary part, we have V and R. So we need to choose the formula P equal to V squared over R. And then at the P in parts, the primary parts, we have V and I. So we just put in P equals to VI. So next step, we just put in the number, the value into the formula. So for P out, we have 15 square over 100, and P in part, we have 120 times 0.2 ampere, and we calculate it and times with 100%, and then we get 94%. So based on our answer, we get the power losses. Just now we calculate, and then we need to find the power losses such as 95% or 98%. So based on our calculation, we have finally find the power losses of ideal transformers. There is 94%. That's all for me. Okay.
Here we will talk about comparison between ideal transformer and practical transformer. So I will talk about ideal transformer. Firstly, ideal transformer are 100% efficiency. Then its current value are equal to 0. Ideal transformer does not have parasitic loss such as iron and core loss. It also have no winding resistance, no leakage inductance, no ohmic resistance, and no I square R losses. As additional information about ideal transformer, the primary and secondary winding share the same core and have the same amount of magnetic flux. Last but not least, since there's no transformer loss, so power in is equal to power out. That's all. Thank you.
Hello, dengar. Bismillah. And now is
Yeah.
my turn to explain to you guys about the difference
Mm-hmm.
between ideal transformer and practical transformer, and my with explain to you guys about a practical transformer. First, 100% below efficiency. It means that this type of transformer efficiency vary between 18% to 99.7%. There can be 100% because there is power loss in the copper resistance. Eddy current in the transformer core, iron hysteresis losses of the magnetizing current, and leak magnetic field interacting with external objects. For the next one, which is a current value is greater than zero. Okay, this is a point has a three factors of why the current value um, um, why the current value is greater than zero. This is have a three factor, and one which is a magnetizing current, and second is iron loss, and the last one is because core loss. Now let's see the third one, which is has iron loss and core loss. This is because leakage induction and winding capacitance are all actually distribute circuit elements. Next point is um, I am the like third and fourth point that I already talked about. And next is about a five, which is this particular transformer, it has I square and I square R losses. This is how to know. This formula is combination from ohm with power law. From that combining, we can see that the loss I square R. This is how to know copper loss. The last point is ohmic resistance drop. The ohmic loss is due to the resistance to the flow of electrons in the electrodes and protons in the electrolyte. Um, and that's all for me.
So for the conclusion is actually Roshu punya part, tapi sekarang dia dekat hospital. So dia dah bagi saya voice, saya playkan aja.
Hello, Assalamualaikum. I'm Rushaida binti Muhammad Fazli and I want to present my part at my presentation as well. So my part
Dengar tak before that? Dengar
Dengar.
Okay.
my part is a conclusion.
Okay, dengar.
So what is transformer? A transformer is a passive component that transfers electrical energy from one electrical circuit to another circuit or multiple circuit. A varying current in any one coil in the transformer produces a varying magnetic flux in the transformer core. Electrical energy can be transferred between separate coil without a metallic conductive connection between the two circuits. So next is what the use of a transformer. Transformers are most commonly used for increasing low AC voltage at high current, a step-up transformer, or decreasing high AC voltage at low current, a step-down transformer. in electric power application and for coupling the stage of signal processing circuit. So next is an ideal transformer has no power loss. All power applied to the primary is all delivered to the load. Actual transformer depart from this ideal model. Some loss mechanism are winding resistance, hysteresis loss, core loss, flux leak, and winding capacitance. The efficiency of a transformer is the ratio of power delivered to the load P out to the power delivered to the primary P in.
Okay, that's all. Thank you.
Okay. Okay, so habis berapa orang bro? 10 orang
Yes, madam. 10.
10
Yes, 10 around.
Alright, thank you very much. Group number 2 from R2B. 10 orang. Yeah? Alright, 10 orang. Okay. So, terima kasih banyak-banyak untuk presentation chapter second topik. Okay, so kita proceed untuk lab lah, radio 2A pula for your presentation. Saya tak nak ambil banyak masa Okay, kita proceed. Radio 2A dah sedia? Radio 2B? Okay.
Dah boleh start ke media? Media dah boleh start ke? Okay.
Saya takut nanti hari tu habis macam hari tu. Lama. Ya, boleh start. Saya tak nak habis macam hari tu lama betul kita present hari tu. Ayuh. Transformer.
So, dengar tak? Hello? Dengar tak? Jelas tak?
Jelas.
Kenapa?
Okay.
Sekali lagi. Dengar.
Assalamualaikum warahmatullahi wabarakatuh.
Jelas.
And hi guys, I'm Aina Kamila
Saya
binti
bayangkan
Muhammad Asli.
transformer power
And
loss
today
tu
we'll talk
kesian.
about Hello? Sangkut ke?
Hi.
Okay, today in our presentation, we'll talk about a power lossless transformer. So, next slide, please. Okay, before we continue, I would like you to know in this content, we'll explain to you the definition of power loss transformer. Four types of ion losses, which consist history, eddy, copper, and stray losses. And then we'll talk about the dielectric and how to reduce power losses. And last but not least is conclusion. So here we go. Next slide, please. Okay. To be short, previous presentation, we know a transformer is a static electrical machine which transfer AC power from one circuit to the other circuit at the constant frequency. And at the same time, the level of voltage can be altered, which means the voltage can be decreased or increased according to the requirement. So I will pass to Aris to continue the next slide.
Hello, my name is Inta Fariza binti Muhammad Fauzi. As we know, a transformer works on the Faraday principle of Faraday Law of Induction. A varying current of the primary winding causes varying magnetic flux, which cause and induce EMF in the secondary coil. I would like to remind back what is EMF in case there are some people who forget. EMF is electromotive force, which is the voltage produced by any source of electrical energy. And then there are ideal and non-ideal in transformer. Let's check it out. Next. As we learn in fundamental of electric circuit, we know an ideal transformer, which is ideally the transformer is perfectly efficient where all the incoming energy is transformed from the primary circuit to the magnetic field and into the secondary circuit. So the incoming power must equal to the outgoing power. In such a case, the efficiency of the transformer is 100%. It means there is no power loss inside the transformer. There is no winding resistance and reactance, which is eliminate the copper losses inside the transformer. But a real or non-ideal transformer, energy is dissipated in the winding, core and surrounding structure. Larger transformers are generally more efficient, and those of distribution transformer usually perform better than 98%. A real or non-ideal transformer has some losses in the form of core or iron losses and copper losses. So when the current in the main winding is changed, then the magnetic flux will be changed so that an EMF can be induced within the secondary coil. A practical transformer and the winding have resistance and reactance, which cause some loss known as copper losses, and core has eddy current and hysteresis losses, collectively known as core or iron losses. Due to these transformer losses, the input power of the transformer is always less than input power. Output power transformer is always less than input power. As we can see in either transformer picture, there are no parasitic resistance, inductance and capacitance, which are nonlinear and complex effect. But in other picture, there are resistance, inductance and capacitance that make power loss in transformer, which is lead to non-ideal transformer. Next. This is the reason of losses in transformer, which is iron losses divided by 2, which is hysteresis losses and eddy current losses, and copper losses, and there are additional losses, stray losses, and dielectric losses. And all these losses will be explained to all of you in detail soon. Thank you.
So hearing me again. Okay. You know what? The power losses that take place in its iron core, we call it as iron losses. And how it is determined in a transformer. So it is determined by the open circuit test or no load test. And these losses are occur in the core of a transformer and are generated due to the variation in the flux. So Ayu will continue this slide. Okay.
These losses depend upon two magnetic properties of material which is present in the core. So they are also known as iron losses. As the core of the transformer is made up of iron and since they do not change like the load, so these losses are also constant. It depends on the core construction and magnetic properties of the core like lamination, winding thickness, lamination resistance, and component density. These losses have two components which is hysteresis and eddy current losses. To determine the iron losses, open current circuit test of transformer is performed. Now we move to Alia Nadira to explain more detail about hysteresis losses.
Assalamualaikum, my name is Aina Nadira and I will be explaining about hysteresis losses. Hysteresis loss is caused by the motion of the magnetic field. This loss happens due to the reversal of magnetism. So where do they actually come from? When a magnetic material is subjected to reversal of flux, Power is required for the continuous reversal of molecular magnets. This power is dissipated in the form of heat and is known as hysteresis loss. Transformer has two states of operation. One is without load and the other is with load. Most of these errors appear when the load is applied on the transformer. When the magnetization force is applied within the magnetic material, then the molecules of the magnetic material are aligned in one particular direction. Hence, the magnetic materials such as silicon steel, which has very small hysteresis loop area, are used for the construction of the core to minimize the hysteresis loss in a transformer. We as an electrical engineer must take care of losses and try to reduce them as low as possible. Next slide. For hysteresis loop, as you guys can see in this picture, the relationship between the magnetizing force H and the flux density B is shown on a hysteresis curve or loop. The area of the hysteresis loop shows the energy required to complete a full cycle of magnetizing and demagnetizing, and the area of the loop represents the energy lost during this process. So what is the benefit of hysteresis loop? This loop gives the retentivity and corrosivity value of a material. Next slide. Okay, so what are the factors affecting hysteresis loss? First, the loop of the hysteresis is narrow, so the material will be magnetized very easily. Next is similarly, if the material doesn't get magnetized simply, then the hysteresis loop will be large. Third, the loop size as well as shape, mainly it depends on the first position of the specimen. And lastly, at different values of B, different materials can saturate, so the loop height will be affected. Next slide. For calculation of hysteresis loss, according to Steinmetz's formula, this is how hysteresis loss calculated by, where PB is hysteresis loss, eta is Steinmetz's hysteresis coefficient depending on material, Bmax is maximum flux density, N is Steinmetz's exponent, range from 1.5 to 2.5 depending on material, F is frequency of magnetic reversal per second, and V is volume of magnetic material. That's it from me. Now I will let Akila to present for eddy current losses.
Okay, Assalamualaikum. My name is Nur Akila Sadrani, and now I will present about eddy current losses. So, before we learn about eddy current losses, we need to know what is eddy current. Eddy current is the current that's circulating in nature and induced because of the relative motion between the magnetic field and conductor. Next. Okay, let me give a brief explanation about how eddy current are produced. You guys can refer to the transformer image on the screen. Okay, first of all, when current is applied to primary winding of the transformer, it produces a magnetic flux in the winding. Okay, during this process, the other conductor material connected with the flux and EMF is induced. Since the core is made of conducting material, this EMF circulate currents within the body of the transformers. So as you guys can see at the slide right now, the circulating things, which is the pink one, are the one that we call eddy current. But this current does not provide anything toward the output power, and it produces a loss that will dissipate in the form of heat energy. So this kind of power losses are called eddy current losses. So briefly, eddy current losses is power losses that exist because of the loss of eddy current that happen when the current is experienced a changing in magnetic field. Next. Okay, now we will look at equation for eddy current losses. This is the equation where Ke is the eddy current constant, Bmax stands for maximum value of flux density, F is frequency of magnetic reversal, T for thickness of the material, and lastly V is volume of the core. Next slide. Okay, as I told you before, eddy current that has been produced does not provide anything toward the output power in the transformer. However, eddy current are useful in these following cases. First one is damping. After that is metal detector, like we can see at the airport. Eddy current also used for induction heating. Next one is electric brake. And lastly, eddy current can be used to detect right in materials. So I think that's all from me. Now I will let Amisha to take over the stage and present her part.
Hi, hello. Assalamualaikum. My name is Tuanar Amisha Arma. So I would like to continue the presentations about a transformer losses, which is copper losses. So what is actually copper losses? Copper loss in transformer is generally defined as the losses occur at the transformer winding. Transformer winding are generally made up of copper material. When current is passed through the winding due to some resistance of winding. Next. So here we are going to see what is actually happen in copper losses. So copper loss is due to power wasted from I square R. So I is the current passing through the winding and R internal resistance. Losses can be reduced by using wire with large cross-sectional area. Next. So here we are going to see formula how to calculate the copper losses, which is PC equal to I square RT. PC stands for total of copper loss and I stand for current and RT is for total resistance. Next. So this is an example of copper losses question, which is a 40 kilowatt ampere transformer with a ratio of 2000 volt and 250 volt as the primary resistance of 1.15 ohm and secondary resistance is 0.0155 ohm. Determined. So the first question is how to find a total resistance. So the formula to find total resistance in this question is RT equal to R2 plus V2 divided by V1 square multiplied by R1. So R2 in this question is 0.0155 plus 250 which is V2 and divided by 2000 which is V1 squared and multiplied by R1 which is 1.15. So the answer of RT is 0.033 ohm. So the second question is to find full load secondary current. To find full load secondary current, what we need is apparent power multiplied by 1000 and divided by V2. So in this question, apparent power is 40 kilowatt ampere and V2 is 150. So the answer for full load secondary current is 160 ampere. The last question is to find copper loss at full load. So as we know, the formula to find the copper loss is PC equal to I square R. So I in this question is 160 square. R total in this question is 0.033. So the final answer of this question is 844.1. So that's all from me. I would like to invite the next presenter, which is Azli. Thank you.
Tadi yang pilih siapa? Nur Akila
Amisha.
Yang sebelum ni tadi Amisha.
Dia baru lepas present ni. Hello? Ha? Siapa? Sebab saya terlalu fokus pada ni, saya lupa tulis nama kamu.
Amisha.
Siapa nama kamu tadi yang baru present ni?
Tuan Nur Amisha Arma.
Syah.
Oh.
Okay. Alright. Okay. Thank you, Misha. So next presenter. Saya fokus pada apa yang kamu cakap. Right. So proceed. Next, meaning of stray losses.
Alin? Alin, okay.
Hello.
Siapa?
Hello. Dengar tak?
Dengar.
Hello and good afternoon to everyone. My name is Jane. Okay. Now I want to continue the
Alin,
presentation
suara
of
sekat.
Tak dengar sangat. Kamu berbisik. Siapa ni?
Azlin, madam.
Ha?
Azlin.
Tak dengar, saya tak dengar. Ada siapa-siapa cakap ke?
Bibi saya tu.
Hmm. Okay, siapa-siapa yang present? Saya tak dengar.
Azlin, madam.
Sebab ada yang mesej saya yang kata tak ada tadi tu. Siapa ya? Azli. Sekejap,
Azlin.
siapa yang masuk saya tadi tu? Sebentar ya. Azim
Azlin.
Azim A-Z-I-M.
Azlin,
Di
madam.
WhatsApp saya ni dia kata Azli. Azli mana? Yang WhatsApp saya ni Al-Azim. Ha? Apa dia?
Azlin. Nur Azlin.
Azlin.
Ha, ya,
Nur
madam.
Azli perempuan. Oh, saya ingat Azli. Yang WhatsApp saya ni Azim R2A. Dia pergi ambil vaksin. So, itu je lah yang tak ada. Yang lain ni saya tak ada beritahu saya apa-apa.
Okay, dah boleh dengar tak?
Dengar.
Dengar.
Ya? Suara kamu lembut sangat. Saya kurang pendengar.
Hello and good afternoon to everyone. My name is Azlin. Okay. Now I want to continue the presentation after Tuan Amisha. So today I would like to explain about one of the losses transformer, which is stray losses. Meaning of stray losses. The occurrence of these stray losses is due to the presence of leakage field. The percentage of these losses are very small compared to the iron and copper losses, so they can be neglected. Okay, next. How to minimize the stray loss in transformer? When there is a less leakage current in the transformer, the stray loss get in the negligible form. So if we try to minimize the leakage current, stray loss reduce. After that, what is the cause of stray losses in transformer? Stray loss in mainly caused by leakage flux from winding, but structure closer to winding will tend to be affected easier by leakage flux. The ratio of stray loss relative to all losses may not necessarily be large, but it is generated in certain areas and may become an issue in the operation of transformer. Okay, lastly, example for stray losses in DC machine. The loss due to sparking between the brushes and commutator segment. Loss due to the armature reaction effect outside the plug distribution.
Tak dengar sangat lah Azim.
Hello?
Ayo. Azim, saya kurang mendengar lah. Suara kamu hilang-hilang. Cuba dekatkan kamu punya suara kamu pada mic. Cuba try.
Dah.
Sebab suara kamu makin macam menghilang, sejak hilang.
Okey, tadi Madam dengar sampai mana?
Hello? Line tak clear eh? Halo, 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 halo. Oh, langsung tak dengar dah. Azlin, Azlin. Mana orangnya? Dah tidak kedengaran dah.
Kejap, madam.
Okey. Lain ni.
Cakap dekat call boleh tak? Nak tak? Ha? Okey. Kita cakap.
Saya cakap kat sini je.
Hello?
Madam dengar suara Alin tak? Mana cakap?
Cuba cakap. Cuba cakap.
Tadi Ayu dengar lah sampai mana?
Cakap kuat-kuat.
Sampai tak example.
For example, okay. Okay, lastly is about example for stereolysis in DC machine. The loss due to the sparking between the brushes and commutator segment. Loss due to the amateur reaction effect that distort the flux distribution and many more are considered
Kejap, Ayu, tunggu kejap.
losses.
Sekejap, sekejap.
Mana tadi? Ayu, tunggu kejap.
Ya, madam.
Dengar tak Ayu?
Sekejap.
Azlin tadi memang lost terus ke?
Tak. Dia cakap dekat call, madam.
Azlin terus lost ke?
Dia cakap dekat call. Saya call dia.
Hello? Yang cakap tadi siapa? Ayu ke Azlin?
Yang cakap tadi Azlin. Saya call dia.
Oh, dia cakap kat call.
Okey. Azlin, boleh bilang balik tak?
Okey. Saya ingat awak yang mentang.
Tak. Okey, bilang dulu Azlin.
Oh, okey.
Okay, boleh. Okay, lastly is example for stereolysis in DC machine. The loss due to the sparking between the brushes and commutator segment. Loss due to the amateur reaction effect that distort the flux distribution and many more are considered as stereolysis. Since they are difficult to measure, stereolysis are considered as 1% of the total output power. That's all from me.
Okay.
Assalamualaikum warahmatullahi wabarakatuh. My name is Putri Hidayah binti Muhammad Yusof. Today I want to talk about dielectric losses. Dielectric loss occurs in the insulating materials of the transformer that is in the oil of the transformer or in the solid insulations. When the oil gets deteriorated or the solid insulation get damaged or its quality decrease, and because of it, the efficiency of the transformer get affected. Next, Ayu.
Okay.
So for the application, electronic components such as capacitor responsible for energy storage properties of the device, high K or low K materials widely used in semiconductors to enhance performance and reduce device size, where K refers to permittivity or dielectric constant. Dielectric materials are also used in display application like LCD. Ceramics and polymers also often exhibit dielectric properties. That's all from me. Thank you.
Alright, thank you Hidayah.
Assalamualaikum. My name is Ayu Nadia Hartini. I want to talk about how to reduce losses in transformer. First of all, to minimize the resistance of winding, thick wire with considerably low resistance are used.
Siapa?
Ayu.
Siapa picture ni? Ayu.
Ya, madam.
Halo. Siapa? Awak present sekali lagi Alright. So kamu punya group ni 8 orang je ke?
9. Tak. 9, madam.
Aina Kamila, Intan Fariza, Ayu Nadia, Alia Nadirah, Nur Akila.
Anisha.
Seorang lagi siapa? Oh, Azim tadi lelaki tu.
Tak. Shazri. Tak, dia tak bentang lagi.
Nur Akila,
Akila,
Amisha,
Anisha.
Azlin, Putri Nur Daya. Oh, ada last, ada. Saya ingat kamu yang last.
Tak, selepas saya ada lagi.
Amisha. Okay. Right.
Okay.
Teruskan. Sorry.
Okay. Second madam.
Teruskan.
The efficient solution to reduce transformer use is to make energy efficient system that has a large core and good quality silicon steel for the core and thicker wire. Next, the eddy current can be minimalized by considering the laminate core. Last but not least, hysteresis loss can be reduced by using alloy like mu metal and silicon steel. Now we move to Shazri Nur Nadira for the conclusion.
Hi, Assalamualaikum. My name is Shazri Nadira binti Shahrin. So for the last slide, which is conclusion. The conclusion that we get from this chapter is transformers are so critical to energy infrastructure. It is potentially beneficial to know more about them and their losses and how such losses can be minimized because they are everywhere. Small improvements to transformers can make a large difference in energy consumption. They are usually regulated by national governments, in fact, to ensure minimum losses. With some small adaptations, transformers can also be used for applications other than voltage changing. For instance, wireless chargers usually function in much the same way as transformers. They do not have a central core, which is less optimal, but by the same principle, the charging coil creates a magnetic field, which induces a current in the receiving coil. In this way, power can be transferred without physical contact, or at least without more complex wiring and connections. That's all from our group presentation today. Thank you.
Okay. Alright, thank you very much. So, semua dah habis present ke? Semua dah habis present ke?
Dah habis.
Okay, so thank you very much for the second group from R2A. Okay. So, R2A berapa orang?
19.
Total kelas kamu berapa orang?
19.
19. 19. R2B pun 19 Right, so okay. Thank you very much to all the presenters. Okay, so for today, okay, kita akan habis lagi sekejap lagi. And then for tomorrow's class, saya belum plan lagi nak buat apa. Okay, sebenarnya tujuan utama saya untuk kamu present, okay, sebabnya saya dah bagi slide presentation pada kamu. Ada ke saya bagi slide presentation dalam group? Ada ke? I lost pula.
Ada, madam.
Assalamualaikum. Dengar saya tak?
Ya, dengar.
Saya punya connection pula yang lost. Okay. So sebenarnya tujuan utama saya untuk kamu present adalah nak bagi kamu idea secara roughly what is transformer that we can cover for this chapter, sebab you are the first student, first batch yang akan belajar transformer yang lain daripada batch-batch sebelum ni. Batch-batch sebelum ni tajuk dia lain untuk chapter 4 ni. So pendapat industri kita tak nak yang belajar yang sebelum ni. Okay, industri dia tak nak tajuk yang sebelum ni. Apa nama dia, tajuk signal tu. So dia nak kamu lebih fokus pada transformer. That's why lecturer kamu ni, kita orang tukar tajuk ni kepada tajuk transformer tahun lepas. Okay, so tujuan saya suruh kamu buat presentation ni, saya nak minta izin daripada kamu untuk saya attachkan your presentation slide yang kamu dah buat untuk 4 group ni. Saya minta izin ni consent daripada kamu untuk saya attachkan mana-mana info yang saya tak dapat. Saya nampak dekat kamu ada banyak info yang kamu cari, saya nak tambah dekat slide yang saya buat. Boleh ke? Boleh ke? So nanti pahalanya kita kongsi sama-sama. Untuk saya tambah dekat slide, alright. And then bila saya akan upgrade slide yang ada, kita akan tambah banyak lagi content. And then slide tu akan digunakanlah untuk semester-semester yang akan datang. So you are the first batch, and then kamu akan dapat ni lah benefit jugalah daripada sini. Maknanya kamu belajar extra lah daripada orang lain. So, boleh ke saya nak minta kongsi daripada kamu ni? Sebab saya akan minta slide ni dan saya akan cedok sikit-sikit daripada slide kamu masukkan dalam slide saya. Boleh ke? Ke kamu ada masalah dari segi tu?
Boleh, madam.
Kamu cakap, madam ni apalah, cari sendiri lah. Boleh ke? Boleh ke? Aku lost pula ni.
Boleh. Boleh, madam, boleh.
Okay, alright. Okay, terima kasih banyak-banyak. Semoga Allah cuba balas kamu punya rasa membuat slide ni and then your presentation. Okay, so apa namanya, saya punya connection macam tak stable lah, banyak loss, kena hilang. Okay, so berdasarkan saya punya pemerhatian presentation kamu, okay, Assalamualaikum. Good evening. Ada tak? Dengar tak?
Dengar.
Jadi saya yang lost pula. Saya punya internet saya slow. Alright. Apa tadi saya nak cakap? Saya cakap pasal apa tadi? Apa yang awak dengar last saya cakap?
Pemerhatian.
Pemerhatian. Okay, so pemerhatian saya. Okay, tahniah kepada semua. You have keberanian untuk present. Okay, harap-harapnya bila bersemuka macam tu juga keberanian yang saya nak. Kemudian saya impress sangat dengan kamu punya slide presentation because kamu tak guna PowerPoint ke? Kamu guna apa?
Canva.
Okay, that's why dia sangat menarik. Okay, so saya pun kena belajar jugalah Canva ni. Benda yang baru dan menarik. Okay, saya ada transformer lagi. Saya dah teringat Optimus Prime lah. Okay. Saya tak ada apa nak komen lah sebab kamu memang cari beyond yang ada dekat dalam slide yang saya beri kamu. So, good presentation. Dan saya dah minta izin pada kamu untuk saya ambil sikit-sikit data-data mana yang saya rasa boleh dimasukkan dalam kita punya syllabus. Kita akan masukkan dalam syllabus kita, apa yang kamu dah cari tu. Okay. Kemudian, so apa lagi? Apa lagi tadi? Ya. Okay. So, saya rasa sampai sini saja. Okay, untuk transformer ni, untuk subjek topik transformer ni, saya akan update semula dia punya, sebab ni adalah syllabus baru saya cari sendiri dalam buku, and then saya update present slide, and then instruction manual. Jadi banyak benda yang saya kena tambah untuk transformer ni. Jadi kalau kamu tengok slide yang saya beri tu, sebenarnya benda tu belum finalize lagi. Saya hanya bagi kamu sebagai guidance sahaja. And then kamu dah tambah-tambah, banyak yang kamu tambah dalam kamu punya presentation. And then akan ada update untuk chapter 4. So, by tomorrow, tomorrow mungkin saya tak akan ajar balik semula transformer ni sampai hujung nanti. Habis nanti baru saya akan ajar. Saya akan terus masuk untuk chapter 5 lah. Okay, transformer ni saya hold dulu. Kemudian, hari tu saya ada cakap kamu balik 1/9 kan? Ada tak saya bagi tahu kamu? Ada. Okey, sebenarnya saya silap baca. 1/9 tu hanya untuk kamu punya senior sahaja. Semester 3 dan 4. Yang kamu balik pada hujung bulan Oktober. Hujung Oktober ataupun awal November. Macam itulah. Waktu kamu kena balik ke sini untuk buat praktikal, and then final, kemudian habis. Kemudian baru sambung semester baru Januari nanti. Okay, Januari, Jun. Okay, jadi kamu ni belajar ni daripada Mei hari tu patutnya Julai, Disember. Sekarang kamu dah jadi Mei, Disember sesi kamu ni. Terlebih apa? 2 bulan Okay. Alright. So, kita dah nak habis belajar pun. Saya pun nanti lepas ni, mungkin seminggu kita akan buat sekali je kelas sebab dah habis belajar. So, setuju ke kalau kita buat macam tu? Setuju tak? Setuju ke? Saya cakap seorang ke? Setuju. Okay. So, nanti besok kita akan masuk pada chapter 5. Kemudian habis chapter 5 dah tak ada apa lagi. And then kita akan tengok dululah. Kita akan study buat tutorial sahaja. Alright. So, I think that's all for today. Thank you very much for your presentation. So, presentation ni saya akan tambah-tambah lah untuk markah test or final kamu nanti. Okay. So, kita akhiri dengan tasbih Faraday surah Al-As. Lupa nak cakap mana yang apa nama tadi tu, mana yang present tadi. Saya minta slide kamu nanti PM saya. Right, so buka kamera, kita akan ambil gambar macam biasa. Okay. Right. Lagi, mana lain? Ada 37. Okay, 2 orang tak ada. Bagus kelas ni, attendance full. Yang tak datang bagi tahu saya. Okay, good. Alright, so buka. Mana? Lain? Oh, Florin. Siapa tu? Boyfriend ke? Terus tutup.
Atlet renang, madam.
Okay. Idola. Yang lain tak letak idola. Tak letak idola, letak dolar. Okay. Semua tak buka lagi ni. Satu. Ya, saya ambil dulu gambar yang ada ni. Senyum. 1, 2, 3. Ayu, kenapa Ayu Nadia, kenapa nampak dahi je? Duduk dahi je. Cik Wazif berada di mana? Di angkasa lepas. Angkasa raya. Okay. Naik 1. Sekali lagi. 1, 2, 3. Right. Habis. Okay, so semua nak pergi masak ke? Ke nak pergi makan? Dah siap masak? Betul pula.
Masak.
Apa dia? Dah siap masak? Tinggal nak makan je. Benda. Apa dia? Alright, so that's all for today. Kita jumpa lagi next class. Okay, bye.
Bye, madam.
Bye, madam.
Bye, madam.
Bye.